Okay, so thank you very much. I'm going to continue from where we left off yesterday. I'm just going to recap the physical points that we were making yesterday, and then I'll stop for questions. Let me just remind you of what are the various things we've said so far, right? So we discussed the geometry of the black hole, and here we discussed the late time isometry. And we discussed the nature of the horizon. I wrote this as two separate bullet points, but I'm now just putting it as geometry uh, or smoothness of the horizon. By smoothness, I just mean that the horizon is like empty space. Okay, I like to use the word smoothness. It's not used by everyone. I just like to say the horizon is smooth. So that's the statement. The horizon is not a special place as you examine it locally. This is what we did in our first lecture. We then looked at the derivation of Hawking radiation. And remember, this was our derivation that told us that if you looked at the horizon, and such a delta function. I'm just writing stuff that I've already written, so it's okay if you don't write it this way. This formula looks a little different for what I've been writing, but I'll interchange the dagger and the creation and the annihilation operator. I've been writing the formula with a e to the minus beta omega on the top, but this is also correct if you write it this way. Then we looked at the naive information paradox. And then we looked at the resolution, which came by saying that pure states and mixed states appear almost identical for almost all observations. Okay. Maybe yesterday I wrote this as 8 bullet points, and I hope, and that was a slight elaboration, but this is what we did till the second to last lecture yesterday. And then, in the lecture yesterday, we started saying there's a refinement of the information paradox, which goes through the principle of ignorance. Principle of ignorance is just a way of saying that, the state outside is given by tracing the state inside. So ignorance here refers to ignorance of the outside observer of what's happening inside. This led to a refinement of the information paradox. And then we said that, we should replace this with the principle of holography of information. And that tells us that if you look at observables in a bounded region, like here, then they can be represented as observables in the complement of the bounded region. So observables here can also have another representation here. Okay. So this I have not yet completely explained. This is actually an advertisement for what is about to come. But we gave a simple example of this yesterday. So I'll just go to the board and then I'll stop for questions, which was the case where I said that think of Minkowski space. No black hole or anything like that. Think of Minkowski space and think of a light ray, and I won't try and do the trick again, which actually, you can think of as hitting Scri plus in the middle of Scri plus. So this was a state which I said was of this form. And this integral over x only went from 0 to 1, okay, acting on the vacuum. And you might have thought that this was a unitary operator that was localized in this region. So no observation here could determine what was happening. But then we discussed how if you computed this 2-point function, which was really inserted here in this region for u in the range minus infinity to minus 1 over epsilon, then you found an answer. I don't remember the factors of 4 pi's right now, which I had written down yesterday, so I'm just going to write a tilde. But the answer looked like, let me put in omega here as well. And you see, if I give you this answer for different values of u in the region minus infinity to minus 1 over epsilon, that's sufficient to reconstruct f of x, as I showed you just by constructing the moments. So even though f of x has support only in 0 to 1, this 2-point function has support even when you put these operators here. And therefore, it's sensitive to the presence of this operator that looks like it's a localized unitary operator, but it's not really localized. Okay, this formula is a repeat of what I wrote yesterday. I even had the correct factors yesterday. Okay, so this is what we have done in 4 lectures so far. And I hope the thread of logic and, these results are at least somewhat clear. This, just to say, this is really textbook stuff. You'll find it in almost all books on general relativity. This you'll find in slightly more advanced books that discuss, quantum fields and curved space-time. This is actually pretty simple stuff, but it's not somehow for some reason in many textbooks. But it really involves just undergraduate, quantum mechanics and statistical mechanics. And, then the derivations that we did yesterday that led up to this are also pretty simple. But maybe we've gone one step further and we are now at the graduate level of using quantum field theory and some properties of gravity. I'm now going to go on and try and give you a general argument for why a result of that kind is true. So from what we do now, it's going to be a little more advanced. As Naboob encouraged me to put all of you in the fire hose. So maybe today's stuff will be a little more advanced. You shouldn't be scared, but at least, so far what we've been doing, I feel if you go back and work on it on your own, you should be able to rederive all of these results yourself. And it would be really good if you were to try and do that. It would help you learn the material. So before I go further and I go on to what I want to discuss today, I'm going to stop and see if there are questions about all this. Okay, so I'll assume this is a post-lunch effect, since I doubt that everyone understands everything. Okay, let's do the following exercise. Okay, let's do an exercise to see if one of the concerns that people might have about stuff of this kind. I said yesterday that even in classical gravity, it was kind of true that if you had something happening in the middle of the space, you could tell it here, right? You have a question? Yeah, go on.
He said that the space black hole is correlated with the Bible. How would different from say the guns? I mean, because depends on the chemical precipitate part they again. Do you know? I see you're on the back.
Yeah, it's remember, it's not entanglement. Entanglement is very common. Okay? Here, a much stronger statement is being made. An observable in the interior has a representation in the exterior. In that, there is no such phenomena that happens with entanglement. When you think of entanglement, this is an entangled pair of qubits, right? The state is entangled. However, if I act with a unitary on qubit 1, like if I act with u1, then no observation that you do in qubit 2 can detect whether or not I have acted with the unitary. You see, this is the statement that if you act with this unitary, where A2 is in, so I've taken this state psi, which is written on the board. I act with a unitary. U1 means that the unitary only acts on the first qubit. A2 means that I measure any observable, anything I like, on the second qubit. This is the same as psi A2 psi. Okay. So no observation on the second qubit can differentiate the state psi from the state U1 on psi. So when you have entanglement, it is not the case that observables in one qubit are the same as observables in the other qubit. It is just the same. It is just the case that they are correlated. Okay. So I can create correlations all the time. Let me create some correlations here. When I put a bottle here, I put a bottle here, right? And when I put something here, I put something else there. right? So this is now correlated, like what's happening on the left and what's happening on the right. I don't know if you can see, right? This is correlated. But if I pick up this bottle, then there's no way someone who makes a measurement here can determine what's happening. It is true that in this state there is a correlation. Okay? If I make a measurement and I find it's a bottle, then on that side will be a bottle. If I make a measurement and I find it's an eraser, on that side also it will be an eraser. Okay? But that doesn't mean that this bottle is this bottle. You see? Here a much stronger statement is being made. It is what is being said is that the degrees of freedom here are those degrees of freedom. It's not that there are independent observations you can make on the left, inside and outside, but rather that those degrees of freedom are fictitious. They're really should be identified with degrees of freedom outside. No. That's a very I know it's a very common way of saying it, but in fact it's completely wrong. I'll tell you why it's completely wrong. Let's say I measured. People say this, right? Oh, look, if I measure this to be down, or I measure this to be down, then I found this to be up. There's a statement they forget to add there. If in the meantime the person on the other side had not acted with a unitary on their qubit. So if I measured this to be down, and if the other person had not done anything to their qubit, then I know that the other person, when they make a measurement, will find up. Okay. However, if I make a measurement that's down, if the other person acts on their qubit with some unitary operator, then of course that it might be down or it might be up. So by making a measurement that is, let's say, I want to say you have this qubit and I have this qubit. Okay. And we are going to play the following game. Okay. I'm going to make a measurement and then I'll tell you what the state of your qubit is. Okay. I can never win that game because let's say I make a measurement and I find it's down. Okay. Then your qubit is up. But nobody stops you from acting with a rotation on your qubit to change it from being up to down. And there's nothing I can do to tell whether you acted with that qubit after the entanglement or not. Right? So when people say if I make a measurement, I know what the other side is, that's very different. That's just a statement that if we prepared this initial state and I made a measurement and you didn't act any further, then I would know what the other side is. Here something different is being said. Here what is being said is that the degree of freedom that you have is I have access directly to that degree of freedom. So you can't hide it. It's like saying that if you acted with something, I would know it. Okay? That's why I gave this example. This example is an example of a unitary operator. Look, it looks like that. You might have thought, if the Hilbert space factorized, that there were unitaries that acted on this part of the space. This is a unitary, see? And this integral over x is just an integral from 0 to 1. So you might have thought this was a unitary that was acting in this part of space. And in a quantum field theory, such a unitary would commute with everything here. But, it doesn't. So the reason I gave this example was it's like that. It's like you are trying to rotate your qubit. Even then I can determine what you have done. In the case of entanglement, you cannot. If you rotate your qubit, there's nothing I can do to determine whether you rotated it or didn't rotate it. Your black hole was never a genuine subsystem to begin with. Like your black hole, really the degrees of freedom in the black hole also exist outside the black hole. Should be identified with degrees of freedom outside the black hole. This is something which gravity kind of forces you to do. It's something we see in many different ways in gravity. Yeah. It's not entangled. I want to emphasize, it's not entanglement. It's identification of degrees of freedom. So please differentiate it from entanglement. Entanglement is something that happens in quantum mechanics. It has nothing to do specifically with gravity. It's just a feature of quantum mechanics. It tells you that there are correlations. It's like the example I gave. That if I measure something here, then there's something else on the other side because I arranged the initial state in a particular way. Now the correlations here were classical correlations. Entanglement allows for different correlations that you can't generate classically. They lead to what are called Bell's inequalities. But at the basic root of it, they're just correlations. If I make a measurement here, there's another measurement there. It doesn't tell me that one qubit is another qubit. This is one qubit and this is another qubit. The dimension of the Hilbert space is 4. Here a stronger statement is being made. It is being said that it doesn't work for qubits, but it is being said that the degrees of freedom in R should be identified with the degrees of freedom in R bar. That's a different statement. Yeah.
What is the purpose of this function?
It is to act with a unitary. And what I'm showing here is you can detect which unitary you acted with. So I acted with a unitary And not only did I detect that you had acted with a unitary, not only is this correlator not the same as it would have been in the vacuum, it is more than that. It is actually, it tells you which specific unitary you acted with. Provided you act with a unitary of this class of unitaries is parameterized by this function S. Okay, is this clear?
See, productions goes the geometry of space time.
No, it's not the geometry of space time. It's well, first of all, we haven't said anything, but yeah, it's more that fluctuations of the metric and of other correlations and of other degrees of freedom should be identified with degrees of freedom there. So the information is stored in some sense, in as parts of the wave function as you go outside. It's not stored in the classical geometry. The classical geometry here is flat space. So it's not that the information is stored in the classical geometry. It's that the information is stored in, quantum parts of the wave function, which extend out to here. That's why I strongly suggest you work this example out and think of the fact that this is a unitary operator, which in a quantum field theory would have commuted with everything here. Okay, let me give you another example just to drive home this point. Sometimes, maybe let me say it another way. Uh, as I said, this is not the classical Gauss law. Okay, but the classical Gauss law is already a simple example of this kind, which tells you that the energy in a region is identified with the metric somewhere else. Okay, so that it's not that the energy is entangled with the metric. That's not what we are saying. It's not like if I measure the energy here, the metric somewhere outside. That's not the metric, but the integral of the gravitational flux because of entanglement. It is the same operator on the Hilbert space. The Hilbert space is such that if you measure the energy in the room, it is equal to the flux of the gravitational field on the boundary of the room. Those two degrees of freedom are not independent. They are the same degree of freedom. You see this? Now, in the case of classical gravity, we have only one such relation, which is that if you give me the total energy, I can equate it with the total gravitational flux. And those degrees of freedom are not independent. In the case of quantum gravity, I'm trying to say it as a much stronger statement. That's like the statement I made here. So in the case of classical gravity, if I took the total energy and I redistributed it, you would not know, the total flux outside would still be the same. So I could redistribute it while keeping the energy the same, and the flux outside might not change. So there's still a lot of degrees of freedom that are local in classical gravity, but not in the theory of quantum gravity. But when you want to think of an example, think of the Gauss law. Don't think of entanglement. Okay, the Gauss law is not sufficient, but it's instructive. That tells you the kind of thing that is happening here. It's not that the matter is entangled with the flux. The energy is the flux. Okay, so this is a new concept. You've heard of entanglement many times, so it's not surprising that you might think this is entanglement. But please try and think of what is being said. It's a new notion. It's not a notion that you might have been exposed to earlier, but it's something that we see all the time in many examples in ADS-CFT, in many different examples. We see this feature. Yeah.
I just want to paraphrase it.
Yeah.
We used to study. So,
No, we have not even established it. I've just given you one example. We've certainly not established it. Okay, I want to give you an example that's related to this classical Gauss law example, right? For instance, imagine that I had in my world two fields. Okay, one was phi, and the other field was phi tilde. And maybe in a theory of gravity, we don't have global symmetries. The people say that, but imagine that these two theories were exactly the same. They were related by what's called a global symmetry. It means that they had the same mass, the same interactions. Everything was exactly the same. Okay, so I take this phi field and I take r to infinity, and it goes to 1 by r times O, which is this O I was talking about yesterday. Remember, I said when you take this limit r to infinity, what I mean is you keep retarded time constant and then you go to infinity. Let's say I take this phi tilde field and you take r to infinity. Then you get, a different boundary operator, which is O tilde. Okay. Now imagine you have this state and you have this state, which is a different state, which is psi tilde. The same function f, yeah. but I replace the field O. Okay. This is a different state. It's not the state psi. But do you see it has the same energy because I said phi and phi tilde are related by a symmetry. So they are really the same, they have the same mass, same interactions with gravity, etc., etc. Therefore, this state and this state have the same energy. They look very similar, right? But this has an excitation of O tilde, that has an excitation of O. So you can think of this as saying, is there a red or a blue marker? Okay. So they are almost the same, but one is red, one is black, one is blue. And I have to make a measurement around and I have to determine is it black or is it blue. Can you see how you might be able to distinguish between this state psi and this state psi tilde? Anyone has any guesses? The question is, I have these same, I'm making this problem slightly harder for our friends who live here, with the Cinderella detectors, which turn into pumpkins. So they have to make these measurements here, right? Okay. So these guys are making measurements and they have to make measurements here. And not only do they have to determine the function f, I now made it, first we were telling them the state was of this kind, determine the function f. There was a lambda also I put actually. Sorry. And this answer was true order lambda squared. But now we are saying, well, the state could be this or it could be that one as well. So can they distinguish between this state psi and that state psi tilde? You'll have to say yep. Well, O and O tilde are not the same, but they're related by symmetry. It's different to say they're the same. Okay? They're the same, meaning they have the same mass and so on. So it's like saying the black and the blue, marker have the same mass and the same interactions with gravity and so on. But they're not the same. They're distinct. Okay? Yeah, O of x omega is an observable operator, and so is O tilde. O and O tilde are two different fields. No, it's simpler. It's the fact that remember these are quantum fields, right? So these quantum fields exist here, but they also exist here. So these operators can not only measure correlators of H with O, but they can also measure correlators of H with O tilde. So you can check that if you measure correlators in the state psi of H with O tilde, you will actually find 0 plus order lambda squared. On the other hand, if you measure correlators in the state psi tilde, then these are the same as correlators in the state psi of H with O. And they're the same as the answer written previously. Okay, I won't write the answer again. That's this answer. Okay. But this correlator and the correlator where you take psi tilde and measure HO, this correlator is 0. So the point is that by measuring, so the point I want to make here is, I've reminded you of the classical Gauss law and how you should think of that as an example of how sometimes you might need to associate operators that look like they're in different places. This is an example of how you might have two states which have exactly the same energy because these fields are really the same. However, you can measure correlators of the energy with other fluctuations, and those correlators can differentiate between these two states that otherwise look exactly the same. They have the same energy. So this is an example of how in the quantum theory you can do much more than you could do in the classical theory. Clearly in the classical theory, there's no way to differentiate this state and this state. So this is an example, even though I want you to think of the classical Gauss law, I want you to remember that clearly you can do more in the quantum theory, and this is an example of how you can do more in the quantum theory. Okay. Is this point clear? Do you want me to explain this in some more detail? Okay. What is not clear? Can you? Okay. So you want me to write the full answer? I can write the full answer. It's look at the equations on the board. You take the state psi and you insert the correlator O. okay, and you put it at this point U. With this point, this insertion U, everywhere I'm writing here, U is in the region minus infinity to minus 1 over epsilon. So what are these observers allowed to compute? They're allowed to make whatever measurement can be made here. So they can make a measurement of h. Why? Because h is the degree of freedom here, because it's symmetric. It's like the flux, so they have to measure the flux, which they can measure right here. And then make an insertion of O tilde. Just to avoid space, I'm going to skip the sphere coordinate. Okay, it's because that's just going along for the right. But in the state psi, if you go through the calculation that we did yesterday, you will find the way we got this answer was that h pulled down a factor of, we expanded this as 1 plus I lambda, and then we commuted h through, and then we used the 2-point function of the O's to get the answer that we got. This is where this answer came from. But if you do the same business with h and O tilde, then the 2-point function you will get will be a 2-point function of an O and an O tilde, because the psi has the state O. So in this case, if you do the calculation, which you should try to do, just repeat the same calculation, but insert here O tilde. Then you will find that the 2-point function will be a 2-point function of O and O tilde. But the 2-point function of O and O tilde is 0. Okay. Remember that what we were using yesterday was that the 2-point function we wrote down this formula yesterday. Remember? And there were some factors of 1 over 4 pi that I don't remember right now. Okay, but if you remember, we wrote down this formula yesterday. It should be in your notes. But the 2-point function of the O tilde with the O is just 0. Therefore, if you repeat this calculation with the state psi and this h, you will find the 2-point function of O with O tilde, but that's 0. Okay? And if you repeat the calculation the state psi tilde on the other hand, then it's exactly the same calculation as the one we did yesterday. This is the calculation we did yesterday. So in the state psi tilde with O tilde, you will get the same answer as we wrote previously, which I haven't written, but if you like, I can write. And I'm suppressing the coordinate omega because that just goes along for the ride. Yeah. On the other hand, the 2-point function, the state psi tilde of h and O is 0. Okay. So this is an example of how in the quantum theory you can differentiate between two fields that have the same mass, clearly cannot be distinguished classically, but can be distinguished quantum mechanically. Yeah, this one and this one. Yeah. You mean I could have written them on the same line? That's true. This? Yeah, they're the same. I just forgot to write it the first line. I could have written this is equal to this. They're both 0. I encourage you to work this out actually. All you have to do to work it out is just repeat the calculation we did yesterday. But put O tilde instead of O. You'll find the answer is 0 if you use this 2-point function. The fact that the O tilde O 2-point function is 0. Yeah. Yes. So here I said 2 kinds of bombs. It can be, in India we have the Lakshmi bomb and the hydrogen bomb. So they both have roughly the same strength. Okay. So they have the same strength. So I set off either a Lakshmi bomb or a hydrogen bomb. And this used to be done Diwali. Now I think they're all banned. When we were kids, we used to have these 2 kinds of bombs, which are both very strong bombs. So you now have to determine from going outside, even though they have the same strength, you have to determine which one it was. Okay, it's not a very good example because in our world, they really both give out electromagnetic radiation. Okay, but imagine in our world, we don't really have these two fields which are related by global symmetries. So I don't know of a very realistic example to give. But imagine that you had, there's not a very realistic example. Okay, imagine there was 2 different kinds of particles or 2 different kinds of fields which were really related by global symmetry. And you could use this to do this. You might have thought of electrons and muons, except they have different masses. So we don't really have a good example in our world. We don't have these fields in our world. Okay, but if you were to imagine a world where there were 2 fields which are related by global symmetry, you could play this game. I set off one or the other. a bomb which produces one field or a bomb which produces the other field, and determine which one it is. In both cases, the observer doesn't actually interact with the field. If they interacted with the field, it's very easy. They would just look at the radiation and see which one it is. So here they have to determine from far away which one you had done. And I'm trying to tell you how you can do that. Yeah.
This is other process because of the problem.
Yeah, you can't do this without the insertion of H. The fact that H was here was very important. Without the insertion of the Hamiltonian, you would never be able to do this. And the fact that H is inserted here is because the Hamiltonian is an observable here, which it's not in others in
For other fields, the same.
in any other field. It is never the case that the Hamiltonian is an observable at the boundary. In no other theory is it the case that the Hamiltonian is an observable at infinity. So what we're saying here is that these people who are here can measure the Hamiltonian. But in no other case does it happen that the energy can be measured at infinity except in the theory of gravity. Okay. Okay, good. So now I want to spend some time just trying to explain how this. So this is a perturbative example, right? This is a nice example. It's fine. We can play these games and we can actually go further with these games. But these games are not enough to say much about what happens to a black hole. They're instructive. I think these games are actually interesting because you can work all this out. If you guys spend some time just trying to work out all the equations you have written, you should be able to reproduce every equation on the board. It will not be very hard, I promise you, if you just have your concepts clear and just use quantum field theory and use the commutator of H with operators and use the Heisenberg equations of motion. You will get all these answers. But this is not really enough to say much about black holes because all the states we are discussing here are light states, right? This state is in the end a low energy excitation on top of the black hole, and I was on top of the vacuum, and I was working to first order in lambda. So if I want to make a statement about black holes, I have to make a much stronger statement. If I want to establish a statement like that kind, I have to make some kind of a non-perturbative statement. Okay. Now there's a problem in making a non-perturbative statement, which is that we don't really understand, many details of the UV complete theory of gravity. Okay. However, I'm going to try and claim that if we make some assumptions about the UV complete theory, then with the help of those assumptions, we can, provide an argument that suggests that that kind of a result should be true in any UV complete theory of gravity. You provided the full string theory, even if you don't understand what the string theory that applies to our world is currently, I should obey the property that is written there, which is the degrees of freedom in a compact region, in a bounded region, should be identified with degrees of freedom in the complement. Okay. So I'm now going to try and give you an argument that suggests that this should be true. Now, even though the first thing I'm going to have to do is that I'm going to have to give up that picture. Okay? That picture is it's a nice picture to keep in mind. However, that picture can never be made very precise. It can never be made very precise because, in the full theory of quantum gravity, you don't expect to be able to define the bulk region R and this region R bar very precisely, right? Because the metric itself is fluctuating. So instead, we are going to try and prove a different result. We are going to think of a space-time which is asymptotically flat. Okay? So this is a space-time which is asymptotically flat. Okay. Such a space-time includes the case of an evaporating black hole. Okay? But for now, let's just consider a space-time which is asymptotically flat. It includes the case of an evaporating black hole because even though we've been drawing Penrose diagrams of black holes that show singularity at the top, in fact, once the black hole finally evaporates, we again end up back in a space-time that's asymptotically flat. And so if you take into account evaporation, then these kinds of space-times include also black holes, evaporating black holes. Okay? And I'm going to prove a statement which is not that statement, but a statement which is going to be a statement on Scri plus. Okay? And I'll explain in a minute why we have to prove the statement on Scri plus. In fact, I already indicated it yesterday. So I'm going to try and prove that this is Scri plus. Okay? And in fact, this is only an asymptotically flat space-time. So all kinds of stuff might be happening around here. Okay? There might be all kinds of stuff happening here. The crosses just indicate that we don't know what is happening in the bulk. We only know that this is the structure of the conformal boundary of the space-time. Okay, so the bulk is unknown. Yeah, we only know the structure of the conformal boundary. Okay, and this is an important thing to do in quantum gravity, because in a theory of quantum gravity, we often, might be in all kinds of different states where the bulk might be doing all kinds of different crazy things. However, we still think it's a good way to proceed to fix the asymptotics, to say if you wait for long enough and you go far enough away from the center of action, then things look like you're in flat space-time. So when we draw a picture of this kind, we are not really in Minkowski space. What we are saying though is that the boundary of the space looks like Minkowski space, not that the space itself looks like Minkowski space. Okay? That's why I emphasize the word asymptotically here. So this is an example. I'm not drawing a space-time which is just an asymptotically flat space-time. What I'm going to tell you is that if you look at the set of observables on I plus, so and I'll define this in a minute, but let's denote by Scri plus the set of, by A of Scri plus, the algebra of observables on Scri plus. The word algebra is really just a fancy word to say that, you think of all possible products and all possible linear combinations. So, you take, and, observables are usually considered to be Hermitian operators. But when we take products and linear combinations in this algebra, we don't care about hermiticity. We allow ourselves to take complex linear combinations. Okay. So you just take all possible operators, let's call it operators if you like, just to avoid confusion. So you take all kinds of operators on Scri plus and look at this algebra, which I'm going to call the algebra A infinity, which is the algebra of operators for u in minus infinity to minus 1 over epsilon. Okay. Then what I'm going to try and show you is that under certain assumptions, every operator, every element can be approximated arbitrarily well by an element of A infinity. Actually, maybe I should call A minus infinity. Okay. Okay. So this is an advertisement for what I'm about to now argue to you. Okay. Which is that think of an asymptotically. So what's the point I made so far? I said that we now want to look at a theory of quantum gravity, and we're going to try and make an attempt to try and say that these results are more general. They don't just work for perturbative cases. So the first thing we have to do is we have to get away from Minkowski space, which is where we were previously. And that's why I said let's think of an asymptotically flat space-time. So that's the word here, asymptotically. This is Scri plus, and I'm going to now explain to you what you mean by the algebra of operators on Scri plus. So you look at this algebra of operators on Scri plus, which is basically the set of all possible observations you can make on Scri plus if you go out very far. And I'm going to try and say that every element of this algebra has a representation in this algebra A minus infinity, which is the algebra of operators, but for retarded time restricted between minus infinity to minus 1 over epsilon, where epsilon is some number that you choose, okay, which is this region here. This is this statement is morally similar to that kind of a statement, because you can think of this region as being the region R and this region as being the region R bar. And what this is saying is that every operator here has a representation in the region R bar. In fact, this goes off to infinity. However, the precise statement is only this. Okay, that's a cartoon. This is the precise statement we are about to make. Okay. Okay. So is at least the form of the statement roughly clear, and its relation to the cartoon we've been drawing. Okay, we keep emphasizing the cartoon because a cartoon is a good way to think about things physically, but that cartoon can't be made too precise because, in a theory of gravity, even those regions are hard to specify. Yeah. Okay, so let me now try and prove the statement. So we need to make some assumptions about the full UV complete theory. Right? When I say assumptions, I mean that these are assumptions about the full string theory that describes quantum gravity in this setting. So the first assumption is, and that's actually an important assumption, is that these algebras continue to make sense. Okay. No, but this is actually an important point. Okay. It's an important point because it's the statement that in string theory we are assuming that even though the dynamics is not well described in the language of quantum fields, if you go far enough away, okay, then you can use the language of quantum field theory to describe operators on Scri plus and speak of operators which are operators with a certain value of the retarded time in this region. Okay. So this is actually an important assumption where we are saying that this is a good language to use even in the full theory of quantum gravity. These algebras, by the way, are closely related to the notion of an S matrix. So this is a statement that the S matrix is something that makes sense in the full theory of quantum gravity. The S matrix is something that should make sense in the full string theory as well. And this S matrix, should in fact be a good and complete observable in the full string theory. That you shouldn't need anything more than that. So this is kind of a subtle assumption, but it's a reasonable assumption. And I'm going to make this assumption. Okay. Now I have to define this algebra a little bit more carefully. And let me define the algebra. Remember yesterday, I defined the limit of a field as you went off to infinity, right? Which was this operator O. So this algebra, what is this algebra? Well, this algebra is roughly the span of all possible products of this operator. So when you think of the algebra, you're saying that don't just think of the field at one point, but think of all possible polynomials in the field and also linear combinations of these polynomials. Okay, so think of all possible polynomials in the field. Okay? In fact, when you want to define the algebra, you have to do a little bit more. You have to think of the set of all bounded operators, okay, and then complete it in a particular way. We won't bother going through that. It's sufficient to think of the set of all polynomials in this asymptotic operator O that I discussed. Okay? This set of polynomials, apart from any massless fields that you have in the theory, should also include fluctuations of the metric. So let me also write, also includes metric fluctuations. Yeah, call. Yeah. No, I don't mean perturbations. I mean the fact that, you can define. So how did I define this operator? The way I defined this operator was, I said you look at phi r omega. This was my definition of this operator. You take this bulk field, you go to infinity, and you get this. When you look at the metric itself, then what you find is that the assumption is that as you take r to infinity, it looks like the metric of Minkowski space, okay, which is, Minkowski. Which is the Minkowski metric, plus some subleading terms. Let me see if I can get the subleading terms correct. I don't want to make a mistake in writing this, so let me try and get phyllots.
So
Yeah. Yeah, that's just what I'm about to write. 1 second, I just want to get my notation correct and not make a mistake, which I do. So give me 1 minute and I'll write down explain what I mean by metric fluctuations. Yeah. Yeah. So the way these fluctuations are usually written is as follows, okay? Plus CAB d omega A d omega B. And this is actually a good expansion to know anyway, okay? This is sometimes called the Bondi expansion at infinity. And it goes as follows. And let me write this term also. into gamma AB. Okay. So this metric is the metric of flat space. Okay. This is just flat space. So when I said that we are in asymptotically Minkowski space, what does that mean? Okay. It means that as you go to r tends to infinity, the metric looks like the metric of flat space. Plus, you look at the du squared term. Okay, the du squared term looked like a -1 earlier in flat space. Now it has a correction which looks like 2m by r. The m definition of m is it is whatever the coefficient of the 1 over r term is. Okay, so the coefficient of the du squared term is changed from being -1 to being -1 plus 2m over r, and m is defined as that operator which simply measures whatever the coefficient of the du squared term is. This is an example of a metric fluctuation, this operator m, because it is measuring the deviation of the asymptotic geometry from Minkowski space. This object is called the shear. Okay. This multiplies, so these d omega are coordinates on the sphere. So this CAB multiplies, the metric on the sphere earlier was just gamma AB, it was just a round metric on the sphere. Now the CAB is telling you that the sphere itself at infinity is deformed. But see, this is subleading from this term. So this was an r square and a gamma. I'm sorry, my handwriting is a little bad, but look here, this is r square and this is gamma. So the leading sphere metric was multiplied with an r squared. This fluctuation is down by a factor of 1 over r. So this is telling you that the sphere at infinity has been deformed. This is also a function of u. This is also a function of u. Okay? This is telling you the deformation of the sphere. And then you can check that the constraints force also that, the du d gamma a term has to be the derivative of the CAB. Okay? But that's not important. And then there are other subleading terms. This term and this term are fluctuations of the metric. In fact, this term is the dynamical fluctuation of the metric. When we talk about transverse traceless gravitons at infinity, they correspond to what is called the News operator, which is the derivative with respect to u of CAB. And this is sometimes called the shear. And this is what tells you dynamical fluctuations of the metric. This is what's called the Bondi mass aspect. Okay, this is sometimes goes under the name of the Bondi mass aspect. So if you were to study gravitational waves, for instance, you would see this expansion, and this is called the Bondi mass aspect. The integral of m on the sphere is called the Bondi mass. Okay, and this is called the shear, and this is called the news. So this is called the news. This is called the mass aspect. Yeah, and this is called the shear. Yeah. Sorry, I don't know why it's called news. Maybe Ashok knows why it's called news. I don't know why it's called news. It's the news. It kind of it's like news. It's the radiation that escapes. So it's this news is capturing the dynamical radiation. Maybe that's why it's called news. I'm just guessing. Okay, my guess is as good as yours. Yeah, yeah.
This is Anitira Shapta Kritas using bow because O is defined on the
No, O is defined in the phi field, and I also want to include these fields. I just didn't want to write lots of different polynomials. Let's also write polynomials of this shear and so on. Let's also write lots of shears. So let's include the polynomial to be CAB UN. Let's call. I'm using a different coordinate. Omega 1 prime, CAB, U2 prime, omega 2 prime, and so on. And also these m's. Okay, so m, u double prime, omega double prime, m of u2 double prime, omega 2 double prime, and so on. Okay, so when I talk of these polynomials, I mean the set of all operators at infinity, which includes, if you have massless fields, these operators O that we defined yesterday, but also these operators that capture fluctuations of the metric that I have defined now. Okay? I didn't want to make this explicit because I wanted to go through it fast, but since you asked, this is the definition of this is what I mean by metric fluctuations. So these are all operators at infinity, and this algebra at Cry plus means you take all possible products of these operators and all possible linear combination of those products, and that's the algebra at Cry plus. Okay, that's what this span means. Is this clear? Yeah. Yeah.
I don't know, but the fluctuation part, does that have anything to do with the altitude? It's like
With what? With the
LTV metric. It's like
what is the LTV metric? I don't know what that is. Maybe it does. This is kind of this is what the metric looks like in the Bondi gauge, and maybe actually this is also associated to Lemaitre and Meissner and so on. I just don't know the term means, so I can't answer the question. Is this metric expansion what is referred to as that? Is this expansion?
Yeah, that also applies to gravitation.
These are gravitational waves. This is called the news. This is the gravitational wave. Okay. I just haven't heard the term, which is just me maybe, but I don't know what the term is, so I can't answer the question properly. But the equation is that this is and maybe it's not just Bondi who should be associated with this, but many other people. Certainly, there's the BMS group that keeps this kind of asymptotic structure intact, which is Bondi, Meissner, and Sachs, who looked at what is the set of symmetries that keep this structure intact. But these are gravitational waves. When you study gravitational waves, this is what you study. This Bondi news is what you study. You study fluctuations of this. So when we study gravitational waves, these are the operators we are measuring. This is where our detector is, and we are measuring these operators. Okay. Okay. Is this are these points clear? So what have I said so far? I haven't said this much. All I said is that we looked at an asymptotically flat space-time, and I tried to define for you the algebra of operators on Scri plus, by which I said you take all these operators and you multiply them in all possible ways. Okay? And what is the range of u? What is the range of u here? This we discussed yesterday. Of all you see, there are these coordinates. Now I wrote u1, u2, un, u1 prime, u2 prime. These are just coordinates that go along with those fields, because all those operators are functions of u and omega, right? So what is the range of u? Exactly, right? So the range of u is minus infinity to infinity, all the ui's. The ui's, the u prime i's, the u, these are all dummy variables, right? This is, you shouldn't care, because this is, I'm just defining the algebra. What's important here is all these variables, the value of u goes from minus infinity to infinity. And what about omega? Omega goes over the full sphere. There's a celestial sphere at infinity, and omega goes over the full sphere. Okay? That's the algebra on Scri plus. Okay? And we are going to assume that this algebra continues to make sense in the full theory. Good. What's this algebra A minus infinity? Is not Scri minus. No. A Scri minus would be a completely different algebra. The algebra A minus infinity that I defined is the same algebra. It's the span of O of u1, O of un. I'm not writing the omegas, okay? CAB of u1 prime, CAB of um prime, M of u1 double prime, M of double prime. It's the same algebra. If I wrote something differently, I didn't mean to. It's exactly the same, okay? With one important difference, that all the ui's are restricted to the range minus infinity to minus 1 over epsilon. Okay? So it looks like this, it's the same structure, but with the coordinates restricted to being minus infinity to minus 1 over epsilon. Look here, this picture makes it clear. This is minus infinity. This is some cutoff that you put. This is this algebra, the set of all operators here. A Scri plus is a set of all operators everywhere. Okay. So A Scri plus is a set of all operators on Scri plus. By everywhere I mean on Scri plus. A minus infinity is a set of all operators near the past boundary of Scri plus, near minus infinity. Okay. You see that? Okay. Yes, the range of the u on this board and on that board is different. That's the difference between them, because A minus infinity is defined as this algebra. A of Scri plus is defined as the algebra on all of Scri plus.
Yeah.
There is an overlap. A of Scri plus looks like it's a superset of A of minus infinity. A of minus infinity is a smaller algebra. It's a sub-algebra you can think of A of Scri plus. There's overlap. A of Scri plus is everything. Okay, so see, it looks like A of minus infinity is clearly a sub-algebra of A of Scri plus, right? It looks like it's clearly smaller, right? It looks like there are some operators that are in A of Scri plus that are not in A of minus infinity, right? in a quantum field theory, if you didn't include, for instance, this Bondi mass and so on, it would be true that A of minus infinity would be a subalgebra of A of Scri plus. However, what I'm now about to show you is that in fact it is not a subalgebra. Rather, every operator here you can approximate in terms of operators there. Right? So you see, it's a surprising result, but it's something we'll be able to show subject to some assumptions. Okay.
Which one is the subalgebra?
That looks like a subalgebra clearly. It's the same set, but with smaller range of U. This is a bigger range of U. So, yeah. Okay, good. So this is the first assumption we need to make. Okay. The second is now the second assumption we need to make is about the Hilbert space. So before I go to the Hilbert space, I need to make an assumption, and the assumption is that the energy is positive. That there's a notion of energy, and the energy, the Hamiltonian, is positive. Okay. This is a pretty reasonable assumption. We can't prove it for the full UV complete theory, but it's reasonable to assume that the energy, whatever it is a positive function on the space. Okay. If the energy is positive, then you have a notion of a vacuum in this system. Right? You have a notion of a vacuum because if the energy is positive, by the way, positive, doesn't mean literally positive. If the energy is bounded below by -10, that's good enough for us. Okay, we'll just shift the energy of everything by +10 and we'll make the energy positive. So positive always just means the energy is bounded below. Okay? Whatever the lowest energy state is, we'll call that the vacuum. Okay. But it doesn't have to do with antiparticles. Antiparticles also have positive energy. Only energy. Okay, good. Then we are going to work in the following Hilbert space, which is given by A of Scri plus on 0. Okay. What does this mean? It means you take the vacuum and you act on it with all these operators. If you remember, this is a linear space. It's a linear space by construction. If you take the vacuum and you act on it with all these operators, you get a Hilbert space. That Hilbert space, I'm going to say, is going to be the Hilbert space in which I'm working. Okay. Okay. So this is the Hilbert space within which we're going to work, which is A of Scri plus acting on the vacuum. Yeah. Okay. So what does this mean? It means you take all these operators, you act on the vacuum within. So those of you who study this is a slightly unfamiliar concept to you. So I'm just going to write it down for now. But one exercise for you to do is you can check in quantum field theory, when you construct the Fock space, you can construct the Fock space this way by taking the set of all field operators and acting on the vacuum. It doesn't matter, by the way, if one state appears more than once in this way, which is fine. You just look at the span of all possible distinct states that you get.
So you do some dissociation and annihilation.
Yes, they will. Well, yeah. So you're right. They will contain both creation and annihilation operators. And so when you add on all possible field operators, you'll get all possible states. Yeah. I'll explain why it's important, but it is going to be important. Yeah, we use it, but we are going to assume it because we don't know what the full theory is. We're going to assume the energy is bound to there. Okay. Now I'm going to prove the first result. Okay. The result is going to be, and this result, by the way, is not that result. Okay. So I want to prove a result which looks like that result, but it's not going to be that result. Okay. Okay. So I'll write down the result and I'll prove it. I won't prove it fully, but I'll tell you why it's true. For all n belonging to this H, that Hilbert space. So any n belonging to this Hilbert space, there exists an xn that belongs to the small algebra, not the full algebra. Okay. Are you familiar with the for all and there exists? This is for all that exists. Such that xn on the vacuum is equal to n, where this dot equal to means that it's true to any desired precision. Okay. So this dot equal to is just a symbol we are making up to say that for every n which is an element of that Hilbert space, I can find an element of the small algebra so that the action of the small algebra on the vacuum approximates this state to arbitrary precision. Okay. Do you see why this is a somewhat surprising result? Okay, this I want to emphasize, this is not that result. This has nothing to do with gravity. Okay. This result would also be true in quantum field theory. Okay. So this is a surprising result, but it has nothing to do with gravity. Please remember this. Please don't get confused. I'm sorry I have to explain this result, and it looks a lot like the final result we want to get to, but it is not the final result we want to get to. It is a result which is true in quantum field theory. It has nothing to do with gravity. Okay. Nevertheless, okay, so with this caveat, please keep this caveat in mind. Do you see why this is a surprising result? It's a surprising result because these states we derived by looking at the action of all these operators in the vacuum, right? So we were allowed to act with all these operators in the vacuum. Someone said you had creation and annihilation operators. So to extract the creation and annihilation operator, I would take this and integrate this with all values of u. And then I would act in the vacuum. Here I'm saying I'm not allowed to act with all values on u. I only act with values of u in minus infinity to minus 1 over epsilon. Okay, I take these same operators and I act on the vacuum and I still generate the same set of states. Okay. So even though I'm acting with a smaller algebra, I'm still generating the same final set of states, at least up to any desired precision. Okay. So do you see it looks a little surprising. Okay. Do you see this? Okay. However, this result is also a result in quantum field theory, and it's something that you can actually go and verify at home without so much difficulty. Okay. No, it's not true for every subalgebra. I'll tell you which subalgebra it's true for. So it's true for this subalgebra. And I don't want to make any statements about every subalgebra. It's true for this subalgebra. What do you mean by cardinality of the generators? The number of generators, that's infinity. So both algebras are infinite dimensional. That's why something like this works. Okay. Because both algebras are infinite dimensional. Rational numbers and the natural numbers. No, that's not a good example. It's more like the rational numbers and the real numbers, but that's also not a good example because you see, this algebra is really restricted to a different part of space than this algebra. One algebra looks like it's integrated. You take all fields and act everywhere. The other algebra is you take fields in a small region and you act in the vacuum. This is, by the way, this result that I'm explaining is related to something called the Riech-Leader theorem in quantum field theory. Okay. So if you open a book on quantum field theory, you will see something called the Riech-Leader theorem. It's an old result. It doesn't usually appear in quantum field theory textbooks, but it's called the Riech. It's related to that. Okay. And I'm not invoking the theorem. The reason I don't want to take the name is that people tell you the Riech-Leader theorem might not be valid for gravity, which it might not be valid for, but this result we are going to prove. It's a version of the Riech-Leader theorem. You can think of it as a version of the Riech-Leader theorem, which we're going to prove. We are not going to prove fully, but I'll prove it for states produced by the action of one field operator in the vacuum. Okay. So what I'm going to prove is, consider the following state. Okay, I'm going to, even though there is an omega coordinate, a sphere coordinate, the sphere coordinate is not going to do much. So I'm just going to suppress it here. So I'm writing O of u, F of u. I'm not writing O of u omega, F of u omega, because we're going to write lots of O's. So we're going to suppress the sphere coordinate. Consider this state, where this integral goes over u equal to minus infinity to plus infinity. Okay. Claim is, we can find different function, some other function, which is almost equal to f. So let's call this f. Let's call this g. So that g is equal to f to any desired precision. Okay. So that, I'm sorry, I'm writing a little low. I won't. And I'm going to write something very simple. So I'll read it out so you can write it. So f minus g is approximately 0. And approximately 0 means I can, by tuning this function g, I can make f minus g as the norm of f minus g. as close to 0 as I like. For those of you who can't see, this just says norm of f minus g is approximately 0. Okay. So this is the claim that just a second. I act with O of u, f of u on the vacuum. I call this state S, and I integrate from minus infinity to plus infinity. I act with O of u, g of u on the vacuum. I integrate from minus infinity to minus 1 over epsilon. And I am going to produce a state that approximates this state arbitrarily well. Okay. This result, as I said, is something you should know anyway independently of black hole information. It has nothing to do with gravity. Okay. It's just a nice result to know. Okay. Is the statement of the result clear? It looks like a surprising result. It's not an obvious result. Yeah.
Does this thing has not pieces of result to the conformal structure?
No. There's no conformal structure involved here. No. Conformal structure of the flat space? No. It's not relevant here. Yeah. What?
You
You could have, in this case, taken some other range also. Yes. It is in, you could have taken it to be infinitesimally small. Yes, you could have, in this case. Yeah. I'll show you the proof. It is counterintuitive, right? But it's true. Yeah, it's true, but it is certainly a form. We are proving it in the formalism of quantum field theory, and it's counterintuitive, but it's true. Okay. And it's true without using any property of gravity. Okay. So, let's prove this result. Okay. So, we'll prove it by contradiction. So, the proof is by contradiction. So, say there is some S, okay, which has the property that it's orthogonal to all states of this kind. So, say it is the case that you cannot generate this S by superposing states of this kind. Okay. I take a superposition of states of this kind, and whatever I do, I just cannot generate this S. Okay. Then say there exists S such that S O of u 0 is equal to 0 for all u in minus infinity to minus 1 over epsilon. Why is this the converse of that? Because imagine that this is a linear space. This space, right? It's a linear space because I can take different functions z and I can superpose them. Say it was the case that there was a state here in this bigger space, seemingly bigger space, that I could not approximate arbitrarily well by states in this space. Then it should be the case that there is a state in this bigger space that is orthogonal to all states in the smaller space. That's the only case it happens that you can't approximate a state arbitrarily well, right? If you have an orthogonal space. If I say in 3 dimensions, approximate all vectors here by vectors in the plane, I can't. Because look, there's an orthogonal vector. Right? You agree with this? Do you agree with this statement? The only case when you cannot approximate a vector in one Hilbert space with vectors in another Hilbert space is when you have an orthogonal direction. Right? If the state f is orthogonal to all vectors of this kind, then it must be the case that it's orthogonal to all O of u for u in minus infinity to minus 1 over epsilon. Do you see this? If it's orthogonal to all O of u, g of u, is that good? So, imagine, say there existed such a state. This is going to be a proof by contradictions. So, by proving this, by making this assumption, we are going to be led to a contradiction which will lead us to the result we want. Okay? So, say there existed such a state, then it would be that this is equal to 0. Okay? But let me insert a complete set of states. This is equal to f of E O of u 0. I'm writing a sum over E, but the sum over E is really an integral over E because you have a continuous number of energy eigenstates, but we don't know the measure and so on. So I'm just writing a sum over E. There's some set of energy eigenstates of states which have given energy, which I've inserted here. Okay? And remember, we assumed that the energy was positive. Okay. So this is equal to this, right? This, I've just inserted a complete basis of states. You know you're allowed to do that. As I said, by the way, what I'm doing right now is a little more advanced. You might not be familiar with it, but it's still something you should be able to follow if you try and do this on your own. Do you agree with this equation? What did I use here? I just used the fact that this u, remember, was t minus r at asymptotically late times. Okay. So whatever the notion of energy is, that energy is something that generates time translations. Okay. And because it generates time translations, O of u is the same as this E with e to the I EU. Okay. Now notice something about this expression. This expression has the property that it is analytic when u is extended in the upper half plane. Do you see this? Do you see why this is the case? Why it's analytic? Because remember, E is positive. So if I extend u in the upper half plane, what does it mean to extend u in the upper half plane? It means to give u an imaginary part which is positive. If I give it an imaginary part that's positive, I produce an exponential damping here with E. So the convergence of this sum, you see this sum, when could it have a singularity? It could have a singularity because you're doing an infinite energy sum here. So it could have given you something singular. But the convergence of the sum improves if you extend u in the upper half plane. You see? Because you get an e to the minus e times the imaginary part of u. Okay, when you extend u in the upper half plane. Therefore, this is analytic in the upper half plane. What do you know about functions that are analytic in the upper half plane? Let's say I tell you I have a function, it vanishes for some reason, it's 0 here, and it's analytic here. What do you know about such a function? No, if it's 0 here and it's analytic here, it's 0 everywhere. Okay, it's just 0. If you have taken an analytic function and I tell you it's 0 in some region, it's just 0 everywhere. Okay. So a function which is analytic on this set here is analytic in the upper half plane, and if it's 0 here, then you can show that it is a theorem in complex analysis. In fact, 0 on the whole real line. Okay, it's just 0 everywhere. This is a property of analytic functions. If you have an analytic function, it's 0 in some open set, it's 0 in some, it's just 0. It has only one analytic function which is 0. Which is 0. Okay. So you can prove this by using the Cauchy residue theorem, but I won't go through the proof. But if you open a book on complex analysis, they will show you that if you take a function which is 0 here, it's analytic in the upper half plane, it's 0 on the whole real line. Okay. Okay. Now, therefore, using this result in complex analysis that you will find in a complex analysis book, what we have proved is, we assume that this was 0 for u in minus infinity to minus 1 over epsilon, which was some part of the real line towards minus infinity. What we have proved is that this implies that this correlator is 0 for all u. But that is an absurd result because f was a function of this kind. So such a function can never be orthogonal to O of u for all u, because if it, in particular, if I take this and I integrate it with f of u, O of u, I should get the norm of f. So this cannot be 0 for all u. Therefore, this is absurd. Because this is absurd, this is false. Okay, so such an f cannot exist. No such f exists. Therefore, this theorem is true. Okay. Now, what we proved here was for when you acted with one version of O. In fact, this algebra A. Okay, let me stop here. Was this proof clear? Not clear. Okay. I'm going to just state the things again, but if you try to work it through, you should be able to work it through. Look, I said, take this function O of u. Consider this set of states. Is the statement of the theorem clear? Let's act with O of u and f of u for all functions f, which have support from minus infinity to infinity. I said such functions can be approximated arbitrarily well by looking at functions that just go from minus infinity to minus 1 over epsilon. How so? We proved it. Say there was a function f which couldn't be approximated arbitrarily well in that way. Then it would be the case that f O of u would be 0 for all u in this range. because it must be orthogonal to all such functions. So there must be some f which is 0, so that for all u in this range. But by the positivity of energy, this correlation function, which is equal to this, is actually analytic when u is extended in the upper half plane. If it is 0 for u in that range and it is analytic in the upper half plane, it is actually 0 for all u on the real line. For all real u. We don't know what happens for u when u becomes in the negative half plane, but in the lower half plane, but we know it's
So what's the meaning of the
real u is just all real u, real life, minus infinity plus infinity. Okay. You see, because it's analytic in the upper half plane, and the real line is the boundary of the upper half plane. So you have a function that's 0 everywhere in the upper half plane. By continuity, you just take it to a real line, it's 0 on the real line. So this tells you that such a function, such a state cannot exist. I know what I said right now is unfamiliar, but I hope the claim of this result is clear. And maybe these proofs that use analyticity are slightly confusing. But I promise you, I assure you, if you go, I myself, I'm not, very good at some of these things. I assure you, if you go and open a book on complex analysis, you will find these results. Okay. So you would, and so they're also explained in many parts of the physics literature. Okay. Now, there's one more thing we need to do to prove the full theorem. The full theorem was erased actually. Oh yeah, this is the theorem. Yeah. Yeah.
Just you plus as you sit down.
Yeah. No, well, yeah. The norm of f cannot be 0. Clearly, the norm. This state is a state which has some norm, which is all these states are positive norm. It's a Hilbert space, nice Hilbert space. So norm of f cannot be 0. If this was 0, then the norm of f would be 0 because I'll just integrate this with f of u and I'd get, and that's of course not possible. So therefore, there can be no such state f. Therefore, f in g has to. Therefore, I should be able to find some g so that f g is as close to 1. This is not f in g. This is f norm of f minus g. It's norm of f. So g is almost the same as f. Yeah. Okay. Now, to prove this result, this is not quite enough because I need to consider all possible polynomials. When you consider all possible polynomials, the argument is not as simple as this. Okay. In fact, you have to look at analyticity in many variables because you will now have to look at functions that are created by acting with many different O's, and you will have to look at functions of many variables. The generalization of this is a theorem in complex analysis that's called the edge of the wedge theorem. In fact, I think this edge of the wedge theorem was in fact first proved by Bogolyubov, not by mathematicians, to prove results in quantum field theory. One place this is discussed is in the book on PCT spin statistics and all that. Another place you'll find some discussion which might be simpler is in Edward Witten's lecture notes on entanglement properties in quantum field theory. I think they're called, from 2018 and 19. Okay. That is also another place to find a discussion, but you'll also find it in this book. This just tells you how to generalize this to states which are produced by the action of multiple O's. Okay. So what we proved right now was not the full theorem, but I'm saying that if you just generalize some complex analysis results, you can prove this full theorem. The full theorem just involves generalizing this to the case where you're not acting with just one O but many O's. Okay. So this is one result that we prove. Okay. I'll just go on for 10 minutes because in fact this is we are almost done. If you have questions, actually go ahead and ask me now. Is the statement of the result clear at least? Yeah, we have not. But now we'll introduce gravity. Good point. Yeah. We have not so far said anything about gravity. Let me emphasize that I said here, this has nothing to do with gravity. I'll keep this up on the board, okay? This is just a result that uses the positivity of energy. Now, where do we need to use gravity? Where we need to use gravity is in the fact that so this is the third assumption we need to make, which is that the Hamiltonian is an element of A minus infinity. It's an element of the smaller algebra. So the fact that the Hamiltonian is an element of the smaller algebra is a statement of the Gauss law. Why is it an element of the smaller algebra? Because the smaller algebra is defined in this. Remember, the smaller algebra is defined here, near the past boundary of Scri plus. This is where A minus infinity lives. Okay, so if you take a Cauchy slice, the Cauchy slice ends here, ends at spatial infinity, and you can in fact show that the limit of the Bondi mass, in fact this h is equal to the limit as u tends to minus infinity. It's the limit of that. Somewhere I had written, I erased it now. The expansion of the metric in terms of the Bondi mass aspect. Okay, and if you take the limit of the Bondi mass as you go off to u goes to minus infinity and integrate the Bondi mass aspect in the sphere, you will get the energy up to a factor of g Newton that I do not remember. Okay, so I'm going to put a hash here, up to factors of g Newton and 8 pi that I don't remember right now. But if you just take the limit of this as you go to infinity, you will find that you get the Hamiltonian. Okay, it's a hash by g Newton. Maybe it's 1 over 8 pi g Newton, but okay, some number. Okay, it I do not remember right now. It's 1 over 8 pi or 1 over 16 pi or something. Yeah. That doesn't matter. It's just a question of how you normalize the Hamiltonian. For what we are doing right now, how you normalize the energy is not important. If instead of the energy you use 10 times the energy, it would not matter in anything we did. Okay. So this tells you that this operator is an element of the small algebra. Sorry guys. H is equal to this. Sorry, I had written A minus infinity is equal to this, which of course is wrong. H is equal to this, and H is an element of the small algebra. Okay. Why is it an element of the small algebra? Because look, it's an operator that lives near minus infinity. Okay. And therefore, by the small algebra included all operators that live near minus infinity. Okay. This is where we included gravity. This requires gravity. And it's an important assumption. The assumption is this remains true in the UV complete theory. This is far from obvious. Okay, this is the fact that this is the case is not clear. It's not an obvious statement, but the assumption is that this fact that the Hamiltonian is an element of the small algebra, which is true in gravity. Why is it true in gravity? Because in gravity, you can prove this result. You can prove this result in a theory of gravity. But the statement is that this remains true in the full UV complete theory, which you can't prove. But it's a reasonable assumption because this is the assumption of the Gauss law. This is the statement that you can measure the mass at infinity. If you go far enough, even if you have strings or branes or whatever excitations in the middle, you can measure the energy if you go off to infinity. Now, one property of an so is this assumption clear? This is here we are assuming the Gauss law. This assumption, this is really the Gauss law. But you see, other forces or other fields all coupled to gravity. So when you measure the mass, you see in a theory in general relativity, this is the definition of the Hamiltonian. In general relativity, this is called the ADM Hamiltonian. This is the definition of the energy. It doesn't matter what forces you have in the bulk. They all couple to gravity, and you always measure the energy at infinity. So the energy is just defined at infinity in general relativity. It doesn't depend on what forces or interactions there are in the bulk. So this is true to the extent we understand gravity. It's a very fundamental feature of gravity. The assumption is that this will remain true, in the full UV complete theory of gravity. UV complete theory of gravity. So the argument I'm making here is it's argument I'm making by taking general relativity and trying to quantize it. Of course, we know that, when you really look at gravity, UV completed, you have to have some string theory where you have to include lots of degrees of freedom, some new degrees of freedom. And we don't quite understand the formalism of how to deal with that non-perturbatively. We don't quite understand how to deal with that non-perturbatively. So the statement is, in whatever formalism that we will find to deal with string theory non-perturbatively, it will be true that you can think of these algebras at Scribe Plus. In these algebras, that's why I said the first assumption was things make sense. There will be an operator defined near the pass boundary that will correspond to the Hamiltonian, as there is in gravity. This is an assumption about the full theory. It's an assumption. It's not necessarily something we can prove. Okay. Okay. For which fields? What do you mean for other fields? What do you mean for if for the electromagnetic field, the energy of the electromagnetic field can be measured at infinity. This is true in gravity and coupled to electromagnetism. You measure the energy of whatever light there is at infinity. That's how it's defined. No. The energy is a component of the metric. With electromagnetism, the metric is not there. This is a metric fluctuation, this M. So with electromagnetism, you just mean that you measure the energy of the electromagnetic field using a metric fluctuation at infinity. Not that there's nothing in electromagnetism that can measure the energy. Just there's nothing to be confused with. It's a Gauss law. You measure the energy. In electromagnetism, you cannot measure the mass. The Hamiltonian is playing an important role here. It's the energy. Okay. I'll take five minutes more because actually now we're almost done. And I realize that here I'm putting you a little bit through the fire hose, but just try and stay, hang on tight. You should at least get the words. Okay. This M was the variable I wrote there before I erased it. Remember when I wrote the metric, I wrote a fluctuation of the Bondi mass aspect. This is the Bondi mass aspect. And this is not the metric. It's a component of the du squared term of the metric. Yeah, I wrote an equation earlier where I wrote the du squared term as being corrected by -1 plus twice m by r. Okay, good. Now, if all this is true, if H is a element of this algebra, then if you measure H, then you can ask what is the probability to get various results. Okay. In particular, you can ask what is the probability to get result 0. That is a projector on the vacuum, which is 0, 0. You have to be a little careful with this projector on the vacuum because, in fact, in flat space where we are dealing with things, there are infrared issues, okay, and the vacuum itself is degenerate. For now, for the purpose here, I'm going to ignore these infrared issues. One way to deal with this is to put an infrared cutoff like you would do in ADS, or to do other things to be careful about the infrared issues in flat space. For now, I'm just going to wave my hands a little bit and say that when you measure the energy, there's some probability of getting 0 energy. And that probability is given by looking at the expectation value of this projector on the vacuum. Because the energy itself is an element of that algebra, therefore this projector on the vacuum is also an element of the algebra. Because the projector on the, if when some operator is an element of the algebra, all its spectral projectors are also observables. When we say H is observable by an observer at -infinity, at u goes to -infinity, what do we mean? We mean they can measure H and they'll get the probabilities of getting different answers. In particular, they might find they are in the vacuum. The probability of getting the answer they're in the vacuum is given by the expectation value of this operator. So if the observer at -infinity can measure H, they can also measure this operator. Okay, now we are actually done. Imagine any state. Okay. Consider any operator. Let me write it here. Yeah.
H is an element of
Yes. H is a unique element of some algebra. Let's say Hamiltonian. Imagine any operator, okay, which is, let's take any operator. Let's not call it O. Let's call it T. And expand it in your favorite basis of states. Do you agree that all operators in this algebra can be expanded in this basis of states? I mean, this is almost a trivial statement. This is a set of all states that we define in the Hilbert space. I can expand all operators in this algebra with some coefficients. I might have an integral rather than a sum, but okay. Look at the result we proved there. For any n belonging to H, belonging to this Hilbert, oh sorry, I realize I'm using the same symbol. This is the Hilbert space H. Sorry, I hope that was not your question. This H is the Hamiltonian H. Okay, I'll put a hat on the Hamilton. Fine. Okay. Okay, this H is the Hamiltonian H. Yeah. Sorry. If I realized I was using the same symbol. When I type this, I use curly H, but I would never succeed with that. Okay, so this is the Hilbert space, and this is the Hamiltonian. Yeah? Okay. So remember that for any operator that belongs to this Hilbert space, I can find an operator that belongs to a small algebra. That's the result one we proved. Even if you haven't followed these results, do you agree that if you give me the result on that board, then this result is obvious, right? Because I can write n as xn on 0 and m as xm dagger, bra m as xm dagger on 0, where x and xm belong to the small algebra. You agree that if you believe the result on that board, then this is obviously true, right? This step. You agree? Yeah. Look here. But this element 0, 0, this is true in quantum field theory. But now this guy is an element, is just P0. So this is equal to you agree with this statement? Because that projector on the vacuum appears there. I just replaced it with P0. I mean, there's nothing to agree. It's kind of obviously true. But this is a product of three operators. It's a sum of product. Sorry, I'm writing something which I'll read out for those who can't read. It's sum of product of three operators from A minus infinity. That's what I've written here. What I've written here is sum of product of three operators from A minus infinity for those of you at the back. Okay. But remember the way we define these algebras, whether they were defined to be closed under sums and products, because it was a span of operators. Okay, the span of operators is by definition closed under sums and products. Therefore, this belongs to A minus infinity, this belongs to A minus infinity, this belongs to A minus infinity. So it must be the case that this whole sum belongs to A minus infinity. So we have proved that any operator in the bigger algebra, in fact, can be approximated arbitrarily well in the smaller algebra. Where did the approximation go? It went in here. It went into the fact that these states you could approximate arbitrarily well, and this is actually an equality. So this shows that any operator in the big algebra we can approximate arbitrarily well in the small algebra, which was a result that was claimed somewhere, although it has now been erased. Yeah. So that was the result we set out to prove. That all operators in the big algebra can be approximated in the smaller algebra. So this was the precise result, that all elements of AF square plus can be approximated arbitrarily well okay. This is the precise version of the principle I wanted to show, which is that operators here can approximate operators here. What we really proved was that operators here can approximate operators here. Okay, this was AF square plus. This was a set of all operators here. And what we proved is operators here could approximate operators here. You can think of these operators, now I'm going to wave my hands a little bit again, but not very much, as being the operators that someone very far away from the black hole can measure. Okay. So now we can go back to the case of the black hole. Imagine there is a black hole in the bulk here. This black hole is evaporating. When it evaporates, something pretty complicated happens here. But you can have observers here who are making measurements, who in fact will know everything that happens to the black hole at late times as it evaporates by virtue of this result. Okay. So by making arbitrarily precise measurements here, they can determine what's happening here. Okay, so what this tells you is that in a theory of quantum gravity, this result that we wanted to prove, We can approximate arbitrarily well, because here we approximated arbitrarily well. We didn't, the precise result was this Hilbert space is dense in this Hilbert space. Because when we proved the result, what we really proved was there was no element of this Hilbert space that was orthogonal to this Hilbert space. That statement actually is that this Hilbert space is dense in this Hilbert space. So we've proved similarly a result there that algebra is dense in this algebra, in this sense.
CEO product CEO. This is type in some right?
No, this is a separate statement. Okay, so let me take a step back. I think I'm running way over time. I'll stop in 5 minutes, or stop in 2 minutes, because see, how did we prove that? What result did we set out to prove? The result that we set out to prove was that all operators in Scribe plus, okay, can be approximated by operators here. This is the result we set out to prove. What did we use to prove the result? First, we proved a result which is still written, has nothing to do with gravity. What we proved is, if you we looked at a Hilbert space, we said, what is a good definition of a Hilbert space to use? You act with all these operators on the vacuum, all operators on the vacuum. Then we said, oh look, we can generate the same Hilbert space, not the same operators, but the same Hilbert space by acting with the operators in a smaller region on the vacuum. Okay. That is a statement which is also true in quantum field theory. Then we said, in a theory of gravity, this is where we use gravity, you have a Gauss law which tells you the projector on the vacuum is an element can be measured by these operators. Whatever we are going to do in gravity, which is special about gravity, is going to have to rely on this side, that the Hamiltonian is a boundary term. So we said, look, the projector on the vacuum is something that can be measured here. Then we said, take any operator in the theory, expand it in a complete basis of states. When you expand it in a complete basis of states, we use this when we use the first result there. Then we use, this is true also in quantum field theory, this result. Then we use the second result, which was the Gauss law, and we replace that with the projector on the vacuum. Really, the second result told us that all these three operators were elements of the small algebra. What would be different in a quantum field theory? Exactly. The PO would exist, but it would not be an element of the small algebra. It would be an element of the big algebra. Exactly. So in PO always exists, but it would be an element of the full algebra, not an element of this algebra. So what is special in gravity? That this is an element of the small algebra. At minus infinity. Exactly. The projector on the vacuum lives at minus infinity. Therefore, you can prove that this operator can be approximated arbitrarily well by an operator in the small algebra. Okay. Actually, it's a good time to stop. We'll have tea. We'll come back and discuss a little more significant for the information paradox. And then I also want to discuss the page curve in the last lecture. I know this lecture has been a bit fast. Part of it was by design, because we were going a little slow in the first few lectures. I decided to go a little fast in this lecture. I hope all of you have at least got the words. These proofs are written down in many places. You can find them and follow them in detail. They're not very complicated. They do involve some new unfamiliar concepts, but hopefully not something very unfamiliar. And I hope you at least got a sense of what is the physics that went into proving this result, that, in the end, all operators here can be approximated by operators here. If you think about it more, you will see it's a very surprising result. It's telling you that all operators here, not just that you can have entanglement, it's really telling you an operator here you can write in terms of operators here. And it's also giving you a prescription for how to do that. So it's a surprising result. So you should think about it and you should try and reconstruct this proof. But what I'm going to do is I'll stop here and we'll come back and discuss implications for the information paradox, and then we'll discuss the page curve in the last lecture. Okay, so thank you. I'll stop here.